All right, once again, welcome to my.
All right, now what do I have? I want to just show my screen on the TV. I click on share screen now.
Yes, sir.
Okay, now what do I click on? Where it says screen or what?
Pick the screen you'd like to share.
Well,
usually the first screen in the upper left-hand corner is a good choice. There you go. Lower that Zoom web browser. There you go. All right,
okay.
Take it away, sir.
Everybody seeing the little Easy Neck Plus box? Okay.
Yeah, I got it.
All right. There's a couple of things in here that I can show you that's already been done for vertical antennas. And so let me pull up, let's see, vertical, easy. I think this is a 40-meter vertical antenna. Yes. So we'll come over here and units, we'll do it in feet. And let's take a look at the antenna. Okay, now this is a case where the antenna is just a vertical antenna, and it is 33.8 feet high, which is a quarter wavelength. On 40 meters, a half wave would be about 67 feet, something like that. So this is a quarter wave antenna, and the which using a ground plane here. And let's see what the ground plane is. All right, in this case here, it's a real simulated real ground. And we can run an SWR plot on it. We'll go from 7.0 to 7.3, and we'll scan it in 5kc steps and see what the SWR looks like. Wow, pretty darn good. Down here at 7 megacycles, the SWR is 1.37 to 1. And it's pretty darn broad, too. It covers the whole 40-meter band. Let's see, get it over there. With less than 2 to 1 SWR. I wonder what the actual resonance is, but it looks like it's a little bit on the low end right in there. But that's okay. That's okay. Now we know what that is. So now we have a vertical antenna that's going to cover the 40-meter band really, really well with a pretty low SWR all the way across the band. And now let's take a look and see what the harmonics for it look like. So we're going to, I'll do it from 6.5 megacycles up to 30 megacycles. And we'll do it every 25 kc. So we'll put that in 0.025 and we'll run the pattern. Doing a lot of calculations here, so it'll take a minute to go all the way up to 30 megacycles. But what you're going to see is the fundamental and the third harmonic. Because the dipole antennas, whether it's in a vertical configuration or horizontal, it's going to give you the fundamental and all the odd harmonics. So here we go. Right down here at this point here, that's 7 megahertz. And right up here, that's 21, which is 3 times 7. So that's the third harmonic. Okay. And it looks pretty darn good there. We've got a very low SWR on both the fundamental and on the third harmonic. So this would make a great antenna for 40 meters and 15 meters. And let's take a look at the plot, see what the plot looks like. And let's see, plot type. Look at the elevation. And that's the elevation. Now this makes a great DX antenna because the angle of radiation is fairly low. So it's going to be shooting most of your signal pretty close out to the horizon. It's not going to be very good for close in work because there's no signals shooting up for the near vertical incidence radiation pattern. So that's why vertical antennas are great for DX, but they're not good for close in on the high frequency bands. Now, one of the other things I wanted to look at here is taking this same, well, you can see the antenna gain right here, the outer gain is actually, it's minus 0.03. It's like 0 dBi gain, which is like about minus 2.5 dB gain compared to a regular dipole. And that all has to do with the ground. Now, if I come over here and put in a perfect ground, and let's take a look at the SWR and see what happens when we have a perfect ground. Na, 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 na. 21, 22. 7, 8, 9. Okay. And you can see with the perfect ground, our SWR is pretty much the same thing. And our beam pattern, now this is with a perfect ground. Now with a perfect ground, your radiation is right along the ground, shooting straight out, the lowest possible radiation angle you can get. And that's one of the things when you're building a vertical antenna to really make a good ground and sit it on a whole bunch of wires, because the better the ground is, the lower the angle of radiation is going to be, and the better it's going to be for DX. Also notice that now with a perfect ground, the gain of the antenna is 5.15 dBi. So we picked up 5 dB a gain just by making a perfect ground rather than a real ground. Now the real ground is Earth. And if I can explain this to you here, if I get back over on this thing here, the ground type, if I were to put in real ground here and high accuracy, where did my cursor go? Oh, there it is. Oh, I need to put more wires in. Okay, so we can't do that. Anyway, you get the idea. Now, another thing that I tried here is I tried taking a half-wave vertical antenna. So I'm going to just change this thing here. I'm going to make the antenna 66, 67 feet high. And I'm going to raise it so that the bottom of the antenna is 1 foot off of the ground. Let's see what we've got here now. Okay, the feed point now, the antenna is actually ending 1 foot above ground. And I'm going to move the feed point to 50%. So what I really have here is a vertical dipole. Okay, it's a half wavelength long, and it's the same thing as horizontal. They just turn the antenna vertical. And so let's see what we get with this, just for the heck of it. Let me run the SWR. And we'll do it from 6.5 to say 7.5. And we'll do it every 5 kc. Run that pattern.
You got 2 decimal places.
Yeah, I see it. Okay, now this is what our antenna looks like. And the resonance right here is 7.015, and the impedance is much higher because we're moving the antenna further away from the ground. And this is more like the theoretical 75, 73 ohms for a dipole antenna. And it's still pretty broad here. I think that the 7 megacycles is about here. Yeah, no, here. Well, 1.5 points, 1.5 points SWR is right in that range. So let's take a look and see what our beam pattern looks like, the plot. And this is our vertical dipole. And you'll notice that the beam angle is down. It was up around 30 degrees when we had the thing sitting on ground. Now we've raised the thing up so that it is a half-wave antenna fed in the middle. And the angle came down, so it really makes a great DX antenna. I wonder what it looks like if we did a 3-dimensional, just for the heck of it. Yeah, you can see it's throwing the signal out towards the side, and nothing coming straight up. And this is what the pattern would look like. Now, if we take this antenna and run the SWR from 7 megacycles to, 7 megacycles to 30 megacycles. And I'm going to do it 0.05, make it run faster. Okay. Now, here is our resonant point at 7 megahertz. Right over here is 21, that's 15 meters. But we're starting to see a hint of a second harmonic over here, which is on 20 meters. And over here, we're starting to see the on 29 megahertz, right up on a 10-meter band. Well, the idea here is when we move the source away from 50% of the antenna, that's how we created a multi-band antenna on the off-center fed dipole. Well, the same principle applies here. If I put the, 36, if I move the antenna to 36, so instead of the antenna being fed in the center, I'm moving the antenna over here, down a little bit. Let's see what it does to the SWR. And of course, when we move it off center, the impedance is going to go much higher. So over here, we're starting to see the second harmonic on 20 meters at 188 ohms. Here is our third harmonic, which we lost a little bit on, and we can see the fourth harmonic up there as well. So if we now put in here a 6-to-1 balance transformer, that would take the 50 ohms and transform it up to 300 ohms. Now, all of a sudden, we're seeing our fundamental, we're seeing a second harmonic, we're seeing the third harmonic, we're seeing a fourth harmonic. We've got a multi-band antenna again, because 3-to-1 SWR is well within the tuning range of the automatic antenna tuners that are in most of the high frequency rigs now. So now all of a sudden we've made a multi-band vertical antenna out of this. Now, and I'm going to show you another trick. I'm not going to do it now because it's a little bit complex to do it in the software. But if we were to take the antenna and lower the antenna by taking this bottom leg and stretching this bottom leg out the side, we would get an antenna that is longer than a quarter wavelength in this direction, but the total antenna length is still going to be a half wavelength, and we're going to pick up all the harmonics. And that's why you see some of these antennas being sold, vertical antennas being sold. I think they're 43 feet, they call them, 43-foot antennas. And if you just have a small leg coming out on the bottom, they'll make a pretty darn good all-band vertical antenna that's good for a DX. No good for local contacts, but it's good for the X. So the same philosophies that we used for the horizontal off-center-fed dipole, we can also use on the vertical antenna as well. I guess that's the message that I wanted to get out. With the vertical antennas, our objective is a very low angle of radiation, and if we can make it multi-band, that's great. Another one that we have in here is a, let me change this. No, we don't want to change that. A VHF ground plane antenna. Now, this is the antenna right up here, okay? And let's see if I can make that bigger. Okay, now you can see this is a ground plane antenna for 2 meters. And it's got 4 sloping radials at 45 degrees angles. And its feed point is right here. And this is your actual radiating element over here. So if we do an SWR check on this, let's run the SWR from, say, 140 megacycles to 150 megacycles. And we'll do that in 0.05, 50 kc steps. Let's run that and see what it looks like. Okay, this is a pretty damn good antenna. The resonant point right here is 142.2. So 144 is going to be somewhere around here. And 148 is going to be somewhere up around here. So the antenna is actually resonant a little bit low. So to fix that, we can change the length of that. I don't want it in wavelengths, I want it in inches. Okay, I'm going to shorten the antenna. 20, I'm gonna bring this antenna down to 420 inches. And let's run the SWR again. Well, didn't like that. It was too much. Was it 430, 425? Let's try 425. The reason the number is so high is it's also representing the height off of ground in inches, and this antenna is really only about 20 feet up in the air. Okay, so we're narrowing in on what that should be. Now it's still a little bit long, so we'll cut it down a little bit. Where's the wires? Make it 423. Run that. Okay. So this antenna now is resonant right at 145.6, getting pretty close to the middle of the 2-meter band. And let's take a look and see what the radiation pattern of this is. Plot type, we want to do elevation. Bang. Okay. That's what the radiation pattern looks like from an elevation standpoint. And the antenna 2.2 dBi, that's about 0 dBd, which is what you would expect. And let's see here, the plot types, the elevation and the azimuth. Looking down from the top, it should be a circle. It is. It's radiating uniformly in all directions. And the plot type, the elevation, shows you that it's shooting the signal out straight out of the sides. That's what you want for a 2-meter vertical antenna, so that you can get this omnidirectional and shooting the signal right out the sides of it. And that's what a ground plane antenna does. And you'll notice that when I changed the frequency, all I was doing was changing the height of this portion. I didn't have to change the lengths of the lower portion of the antenna, because in effect, it's like a ground uniform there. And this is the quarter wavelength portion of it right here. And the SWR is pretty darn low. Got a good antenna there. So anyway, that's kind of what I wanted to show you guys tonight, that the theory that we talked about for horizontal antennas is also applicable for vertical antennas. You can make multi-band multi-band antennas out of them. One thing that I wanted to try, and the third harmonic of 2 meters is 440. If you take 144 times 3, it's 432. So I've often wondered, if I just took a standard 2-meter vertical antenna, would it work on 440? Let's find out. So I'm going to do the sweep up to 500 megacycles. That's a big change, so I better do it in 200 kc steps. Na, 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 na. All right, we're narrowing in on 500 megacycles, and we'll be able to see if there's any other resonances on this. By golly, there is a resonant up here. Look at that. 451, 145.6, the third harmonic. It should work on 432. Don't need a dual band antenna. Just take a regular 2-meter vertical antenna and it'll work on 440. Let's look at that. Let's just do it from 420 to 460, and we'll do it in 50 kc steps. Run that SWR. Okay, and let's go to this one here. And look at that. We have ourselves, this is a 452 megahertz. This is 446. We've got ourselves a dual band antenna. Why spend the money for a dual band antenna? Amazing what this antenna theory does. Okay, at this point, maybe if Lee can turn everybody's microphone on and see if we have any comments or questions or complaints or whatever. I guess everybody can put their own microphones on. All right, any comments or suggestions or thoughts or questions?
It's Rob here, KC3QPC. Now, this is very interesting considering that another month or two, I do want to put up a roof antenna, and makes me wonder if I do need to get a dual band antenna, or if I should just be looking at a 2-meter.
Yep. That's exactly right. And this also applies with your mobile antennas. If you put a 2-meter whip out there, just a plain 2-meter whip, it'll resonate pretty close to up in the middle of the FM portion of the 440 band as well. It'll work. It really will.
Yeah, I do have a dual band mobile glass mount because that's all I wanted. And I'm getting like 1.2 SWR in 2 meters, and it's only like 1.6 in the 70 centimeter.
Yep. Yep. It'll work damn fine, splendid.
Mm-hmm.
Now, some people will try to tell you, well, this is a 3 half waves antenna. Well, yeah, that's correct. That's what it is. Just a single wire sticking up in the air. The little curly Q they put in the middle, I think, is more
for looks.
Yeah, well, it shortens the antenna a little bit. That's really the only effect. You're doing center loading on it, so you're shortening the antenna a little bit, but that's all it's doing. And
Okay.
So in any event, that's pretty neat, huh?
Hey, Hank,
Absolutely.
Yeah.
could you talk a little bit about cross polarization with VHF going up through HF? Where does that come in play?
Somewhere between 10 and 6 meters. Down on the high frequency bands, once the signal gets up into the ionosphere, the direction of the polarization gets mixed up. It really doesn't make any difference. On VHF, it makes a tremendous difference. On 2 meters. You could be as much as a 20 dB loss if you're doing a cross polarization, trying to talk to a vertical antenna with your antenna being a horizontal one. But that break-even point depends on the sunspot cycle, on the propagation, how ionized the ionosphere is, but somewhere in that range, 30, 40 megahertz. 30, 40 megahertz. No difference.
Thank you, Hank.
Anybody else?
Yeah, Hank, it's Robert.
Yeah, hi, sir, Robert.
Quick question. The radiation, 3D radiation pattern at this harmonic, the 70 centimeter. Could you run that? Because I'm wondering, does it have multiple lobes, or is it as uniform as the fundamental?
Well, we can take a look at that.
Yeah, I'm curious about that.
That's what it looked. Well, let me see. I want to see what it is on 440.
Yeah, you're at 146.
Yeah, let me change the frequency here. 445 here. Okay. And now let's see what the plot looks like. That's what the plot would look like on 440.
Okay, so it's not a bad pattern. But it is not as uniform.
Yeah.
Okay.
And this again is because we don't have a perfect ground. We have those 4 radials hanging down on the thing. Good question, though, Robert.
Yeah, I got a second one if you got time for it. I was inferring from what you said that depending on the frequency, you were showing, how you were getting the harmonics to show up as you move the feed point.
Yeah.
I'm not sure this is true, but that you the input impedance changes with what frequency you're at. In other words, just because you're geographically at one point doesn't mean your impedance is the same when you go from one band to the other. Am I correct?
Yes and no. If we look at our geez, I lost. Here's the SWR curve. Hold on. We bring this up here. I can show you that the impedance here on 440 is 70 ohms. With a 1.42 to 1 SWR. That's assuming you're using a 50 ohm drive. If you use a 75 ohm cable, get an even better match. But yeah, the impedance on horizontal antennas is very, very much a function of height above ground. But on vertical antennas, it doesn't change that much. If you use loading coils to shorten the length of an antenna, a vertical antenna, for instance, in theory, an 80-meter vertical antenna should be half wavelength high would be 40 meters. That's 120 feet. Okay, something like that. That's really getting up there. So very few people can afford that kind of a vertical antenna. And even a quarter wavelength would be 20 meters high, 60, 70 feet high. So to shorten the antennas, people put loading in them. There's 2 ways you can put loading. You can put capacitive top hats on the top of the antenna. That'll lower the frequency. Or you can put loading coils in the center of it or down at the base. But anytime you try to lower the height of the antenna electrically with a capacitive top hat or loading coils, the drive impedance nosedives down to around 5 to 10 ohms. And that's when it really becomes important to have good wires and everything else, because you don't want to have any resistive loss in there as well as the impedance law.
All right, thanks, Hank. No, I was not to sidetrack this, but I was playing around with some homemade J poles trying to do dual band, and I noticed that the impedance match was different between the two bands, and this explains it. So I appreciate that. Thanks.
Okay. Well, that's all I got for this session, guys. Any other questions, or we can wind it down? Lee, are you still on there anywhere?
I'm sorry, Hank, I've got another meeting going on.
Oh, okay.
Yes, I'm still here, sir.
All right. Well, I appreciate everybody checking in, and I think that these little video sessions that we're doing, it's much easier to explain something than just throwing out a whole bunch of words. That we can have some cartoons to look at too. So, anyway, thanks for checking into the net, everybody. It's been a good net and a good session, and we'll see you next week.
All right.
Thank you, Hank.
No problem.